Alright guys, so the goal of what I'm trying to do today is introduce you to a different type of vector operation as opposed to just adding, subtracting, multiplying, dividing. This operation, which is, as you can see here, is called dot product, is used in physics and engineering quite extensively. Mathematically speaking, it is used in calculus quite a bit as well. So you'll see this in any type of math field. You're going to see this multiple times throughout multiple courses. So first off, I'm going to show you what it is. I'll show you kind of what it does briefly, and then I'll even finish up with showing you how you can even use dot product on your test this week, so you'll have that opportunity. So to get started here, let's get going here by just showing you what dot product is, what the operation looks like, and it involves these two vectors. So I have vector A written out and vector B written out. So we're just going to go ahead and use this as the name for our vectors, and this is what dot product is as an operation. So A dot B, so vector A dot vector B, and by the way, when you see that, understand that this is a dot product, which doesn't actually, I know it can be confusing. You see this dot and you think multiplication. This is not multiplication, so don't treat it as that. And again, I know dots can be multiplication, just in this scenario with vectors it is not. So this just means I'm doing a dot product. So this is what the dot product is. It is going to be, as you write this out, it's going to be A1 times B1, so the horizontal components of each vector multiply together, plus A2 times B2. So be aware when you see this, your answer is a scalar. Again, a scalar is nothing more than a number. I'll explain kind of what that number is in just a second. So another way, I should say, that you can find a dot product, and this is very similar to what we did with our regular vectors. We had our regular component form with horizontal and vertical components, and then you had the trig form. Well, there's a similar form like that with dot products. You can do it in terms of a trig function. So the other version that you can have is A dot B equals magnitude A times magnitude B times the cosine of theta. And again, this is the form that you use, obviously, if you have an angle, and the other one we didn't. So what you can now do with this form, I'm going to try to show you briefly, show you again what we're kind of doing here, so you know what, this seems kind of like random math. It's not completely random. I mean, it seems random at first, and it's just one of these things, again, like unit circles seemed random. Why am I throwing all these angles and numbers and all this out there? But there's actually, again, a very good reason why we do that. It becomes very useful having this knowledge when we get into other types of operations. Dot product is kind of like that. So to kind of set this up and try to give you a brief explanation of what's going on here, I'm going to write out two vectors. I'm going to write out vector B, and I'm going to write out vector A. And again, there's no particular angle here. I'm just going to draw two, and this is what I get. So again, the part of the setup is writing the magnitudes of each, because that's part of the formula, and writing the angle in between them. And I'm just kind of setting up what I already have up above with my dot product. So now I want to figure out, okay, well, what do I do? What does this thing mean? Because we know this represents the dot product, so I'm going to focus in on what that means, because we know what those things are, but I want to show it on a picture. So here's how we start this. First thing you're going to do is take, it doesn't matter which vector you choose, I'm just choosing vector B. I'm going to draw a right angle with the other vector. Again, I could have done that with vector A if I wanted to. I could have done that. Just pick one. Okay, so that's the one I decided I'm going to pick. And I'm going to set up a right, basically I'm trying to get my cosine. What does cosine theta equal? Well, this is what cosine theta equals. I'm going to focus on that right now. Cosine theta, again, just knowing SOHCAHTOA, is adjacent over hypotenuse. So I know adjacent is this side length right here. So I have that piece. I don't know what that means right now. I mean, I know what it means, but I don't know what it means. But I know what h is. H is my hypotenuse, which is the magnitude of b. So I have cosine theta equals a over the magnitude of b. So I'm going to move that b to the other side. So I now have b, or magnitude of b, cosine theta equals a. So now I want to say, okay, well, I know now if I'm looking back at the formula, I'm going to pull it down here. And again, I can copy and paste this, so I'm going to do exactly that. And I want to break down this formula a little bit. So I know that b, and I'll change colors as well here, I know that this is going to equal that a value. Well, this a value has a name. This a value is called a projection. It is the projection of vector b onto vector a. So kind of like what we do again with our horizontal vertical components, when you get a vector, you have two components that you use to get to the terminal point of that vector. Now if they're horizontal and vertical, we can just use our component vector form, but if it's not, you know, we're using some other things, put it that way, to put it lightly. But this represents one of those two components. It represents the component of vector b that is going in the same direction as vector a. I'll say that again. It is the component of vector b, because there's, see, I have those two components drawn that you would use to draw vector b. It is the component that is facing the exact same direction as vector a. So what I'm doing when I'm doing dot product is I'm taking vector a, so I'm taking the magnitude of vector a, and I'm multiplying that. So I'll even put a little x there. I don't want to put a dot because I don't want to confuse you with that. But I'm multiplying it by the projection of vector b onto a. So in other words, how much of that force from vector b is going into vector a. I want to know how much of that is occurring. And that's what the dot product gives me. One common use, I'm not doing an example of this when I'm in physics class, but one common example of that is the work formula. You use dot product on this one. And work represents force, which you usually use as a vector, times direction. And again, if you've done that, you may be like, oh yeah, you know what, I have done dot product. If you haven't, then you maybe aren't in physics, or you haven't gotten there. I don't know exactly when you get there, but you'll be using dot product when you do. So that is one very common use, and that's kind of what, you know, again, just all I'm trying to do is just give you an introduction of why dot product may be useful. And this is literally just the tip of the iceberg in the sense that there's so many uses throughout calculus, engineering, and physics. Again, engineering kind of takes the calculus and the physics and puts it together a little bit anyway, but, you know, anyway, so we're good. So where we're at now, again, we've just kind of seen dot product. Maybe you've used it before, maybe you haven't, but I want to go through some basic operations with dot product. The second one is something that you can use on your test, as I said before. So anyway, finding the dot product here, I'm just going to give you two vectors, and we're just going to find the dot product. And this isn't using theta or anything like that. So it's going to be that first formula that we were talking about. So if I'm going to find the dot product between v and u, I'm just going to go dot product, v and u, and remember our answer is going to be a scalar. So I'm going to take my horizontal components, and if you don't remember the formula, hopefully you have it written down. I'm going to multiply, move it up out here a little bit. I'm going to multiply my horizontal components and my vertical components, and I'm going to add those two products together. So if I do that, I'm going to get 3 times negative 4, and then I'm going to get 6 times 2. And again, we want to go ahead and add those products together. So hopefully you've done that. You get negative 12 plus 12, and we get 0. So this is a dot product, but I wanted to pick this one because, again, I'm trying to cram a few concepts in with you today, and I want to talk about this particular dot product. We got a dot product of 0, and the question is, well, what does that mean? So I'll write that down. What does that mean? Well, it means something kind of neat. So let me show you. I'm going to go ahead and draw this picture, quick sketch of it, but I want it to be somewhat accurate based on what I want to do with it. So I'm going to try my best here to get something close to what I want. So I have the points 3, 6. So 1, 2, 3, and I'm going to go up 6, 2, 3, 4, 5, 6. So 3, 6 looks something like that. So I have this first vector. So there's one of my two vectors, and then I have the vector, and I have, what is it? Negative 4, 2. So I'm going to go left 4. I don't know why I didn't draw more space there, but whatever. So negative 4, and then up 2. So there is that vector. And what is actually happening when I say, what does this mean? Well, here's what's happening. This angle, again, I want to try to draw it somewhat, somewhat to scale, but this is a perpendicular line. They should be perpendicular. What that means is that there's no projection. If I try to draw a projection here, try to draw a right triangle, I don't have one that I can draw. And if you remember, I went up here and I drew a right triangle. I kind of drew it down onto the other vector. Well, I can't do that here. So what that means is there's no projection. Again, you think about it with in terms of work too. If I'm pushing something perpendicular to the motion, think about how that would affect your actual work, how much work is being done. You can kind of if you've done work. If not, don't worry about it. But you can kind of think about it, in terms of perspectives if you've done work problems before. But here's what this really means is I have no projection of vector B onto A, or in this case, I forgot why I didn't label them. Probably shouldn't have done that, but I guess it was U onto V or V onto U, depending on what projection you were trying to make. This has a name, just so you're aware, and these are going to be called, and if you have perpendicular vectors, so that's what we have. So perpendicular vectors are called orthogonal. I should probably spell that right. Orthogonal. So again, perpendicular vectors are called orthogonal. And that means that they're obviously perpendicular and they don't have a projection. They can't project onto one another, which also, like as I said, you bring it back here, that means you have a dot product equal to 0. So again, that's a cool little aspect of dot products. But again, sometimes you obviously get a value for your dot product, and if you do, great. If you don't, that means they're orthogonal or they're perpendicular vectors. So last thing, talking about angles and angles between vectors. Now again, we know if we can figure out if they are perpendicular or not, but there's also another formula here we can use to find the angle between vectors. And notice we've already been doing the angle between vectors, but this is another route to get us there. So I have two vectors here for you, 6, 2, and negative 4, 3. We're going to find the angle between those vectors using dot product. So a formula, again, that comes off of the dot product is this one right here. And all we have to do is plug in, and we can find the angle between our vectors. Now in order to do that, we have to find the dot product, so A dot B. So remember what that means. We're going to go 6 times negative 4 plus 2 times 3. I'm taking the horizontal vertical components, I'm adding those products together. And that is divided by the magnitude of each vector. So that's going to be the, and they're being multiplied. So again, I don't, normally if you don't have vectors and we're multiplying here. So the magnitude of vector A, that is going to be the horizontal components, or the horizontal vertical components, the a squared plus b squared. So it's going to be 36 plus 4 for vector V. And a squared plus b squared is 16 plus 9 for vector U. And again, I'm just connecting those two right there. And now we just simplify everything. Remember, this is all cosine theta over here. I just need to figure out what cosine theta equals. So that's negative 24 plus 6. And then I have the square root of 40 times the square root of 25. That's going to simplify all this. So negative 24 plus, I don't know why I wrote negative 24 plus 9 on my other sheet that I was doing before, but this is negative 24 plus 6. I mean, you obviously know how to add. Why am I even using a calculator? But I'm getting myself ready for the next step. Obviously, this is negative 18. We know how to add numbers, but what you're going to have to do later is you're going to have to plug this into your calculator. So you might as well have your calculator ready to go as you do this. This is negative 18. But over here, we're going to get some numbers. You don't really have to, because we're going to have to use our calculator here. That's why I was just getting it ready. You don't have to actually multiply and simplify these radicals, because I'm going to plug into a calculator. So I'm just going right now 40 times 25. Or you can go, actually I won't even do that. I'm going to go 5, because I know the square root of 25 is 5. So I'm just going to go 5 radical 40. I can simplify the square root of 40, but because I'm going to plug this into a calculator anyway, there's really no reason to do it. So here I go. Theta is equal to cosine inverse of negative 18 over 5 radical 40. Actually, I should probably use a calculator on the screen so you can see me do all this. So I'm going to actually bring that out, and you'll see me work this out. Obviously, make sure you're in the right mode. I am in degree mode, so I'm good to go. So I'm just going to go negative 18, and I'm going to take that and divide by 5 cosine 40. I'm just doing this separately so I don't screw it up. So I got that number, and I'm going to do cosine inverse of that number. So that's going to give me approximately 124.695 degrees. And that's going to be the angle between those vectors. And again, it's just formulaic. So that's another little method you can use to find the angle between vectors. And again, there are way more applications than I did here, but I just wanted you to obviously at least see and understand and notice that there is another operation we can do with vectors. It's called dot product. So hopefully that was something that you will be able to use as you progress through your math and your physics career.